Good morning. Well, today's presentation is about network automation. I'm speaking today about a technology that will allow you to build a network, fully automated network in just a couple of minutes. Supposedly, it should make your life much easier, much simpler, or that's how the designers thought it should be. I work for a security company based in Heidelberg, Germany, and for this topic of today, I have been working on throughout my master and bachelor thesis both. So what is this all about? Haven't we all had that problem that we sent a field engineer to the customer side just to install a new router and he didn't have the running configuration with him? Or we mistyped something and we kept days and days trying to troubleshoot it, but we don't know where the problem is? What if I said to you, all of that is from the past? What if I said to you that now routers can be like USBs, plug and play. You just put it and it works. Nothing much, no hassle, no misconfiguration, nothing at all. This is for the first part of today's presentation. For the second part, the question comes, are we really in control of our network? This technology is a new one, but it's by Cisco and it's proprietary. We don't know what they are doing with our networks. We don't know what they are running through it. And that's why we have the second part of today's presentation. It's about reverse engineering, understanding how the protocol is constructed. In the last and the final part of today's presentation, if you are into security or into life hacking mode, we will have real routers. We will try to launch real attacks and see whether the network will withstand our attacks or not. So keep it up, buckle up, and be ready. It all started in 2001. With IBM. They had this idea. Systems are getting more and more complex by time, and we wish if systems were smart enough so they can manage themselves. With this idea in mind, they wanted systems that are able to configure themselves. You don't need to configure anything. They should be smart enough to configure themselves. They should be smart enough to protect themselves. Even they should heal from any broken processes by any means on their own. Well, this was an optimistic view how future systems should be. And in 2013, people from IETF and from Cisco sit down together and started to write the specifics for this new network. They called it the autonomic network. What was their vision for that? They had this idea. We only need one single device and everything that's connected to that device should be connected on its own. Okay, this sounds a little bit optimistic. But what about for example, how many configurations should I configure this single device? You are saying this single device should build the whole network. So how much configuration do I need to do here? Well, they are just 5 commands. Just 5 commands, you write it on the device, and after that, everything connects to it, works. Simple and easy like this. How many configuration lines do I need to put on the others one? Completely nothing. Just connect, works, USB. This sounds to be somehow so much optimistic, so let's try to see if it really works. So for the people who are aware of Cisco devices, I just got a totally new device here with me. I just erased everything on this device just before I come here. And supposedly all what I try to do here is I try to connect it to this single device and see what will happen. Supposedly, as per Cisco, this device should be configured without any hassle from my side or without me doing anything. I have kept it turned on for quite some time now, so I hope it works because usually it just, once you put it, it should work on time or, yeah. Here we see that although I'm not configuring anything, I'm seeing some information is sent to that device. I can see that some interfaces are becoming up on its own. I can see, okay, it's just taking time. I can see that there are some keys that are generated here. I see that some interfaces even became up. And everything is generated while we are speaking. I didn't configure anything. I didn't put anything. This is just a brand new device that you just bought. And still, there is more and more configuration being sent while we are speaking. So to have a simple idea, even I can see ton of interfaces coming up here. I would like to see what are the interfaces, for example, that are configured here. I can see now, I got an IPv6 address. I found 2 or I have multiple interfaces were created for me. Everything is up and running. At least now, if you are sitting in your center, you can just connect to your device and put whatever you would like to put on. I didn't configure anything. Connect and works. So what do we get from this? Routers are no longer that complicated thing that you need to configure more and more. No, plug and play. It's simple like that. If it's a brand new device, you don't need to configure anything at all. And if it's a device that already have a configuration and has been running for some time, all what you need to write is just a single command. In order to understand a little bit deeper about what happened in the background once we connected the devices, we will have a brief overview over the technology, understand what are the main components of it. Cisco divides what we have just seen into 3 phases: a channel discovery, adjacency discovery, and in the end, the secure channel. For the channel discovery, it's somehow like this one single device, which we call the register, is sending layer 2 probes, searching. Is there any autonomic device around? Just sending, sending, sending. That's all what's being done here. Once it finds the device, we start with the adjacency discovery. This register starts by saying, well, I support this domain or this network. Would you like to join mine? In order to just determine something like this, this register has a whitelist of the allowed devices to join. Because we are speaking about brand new devices, what's there in the whitelist is just the serial number, nothing more. Well, if you are allowed to join, then perfect, we will generate you a membership card, which we call the certificate here. But if you're rejected, then thanks, we will just be like layer 2 neighbors. This is a UDP service running on port 4936. We just need to know that everything here is IPv6 based. To have a simpler idea, we can see it as the following. The register starts with, I support domain X, whatever it is. And the enrollee replies with, I'm from domain, whatever, Y. Well, if there are 2 different domains, then they shouldn't communicate with each other. Maybe he is from other company, it's a malicious domain, they shouldn't connect to mine. Only devices can be part from one domain. If the domain name is empty, it means, well, I would like to join yours. Me, as a register, I'll just check my whitelist. Is this device allowed to join? Perfect. If it's allowed, then I'll send them my membership card or my registered domain certificate. And I will ask them to generate a key for me. We will understand the significance of this certificate later. So once they generate the key for me, they send it back, and I'll try to issue them a certificate. You can make your device issue the certificates on its own, and we call it here certificate authority, which is local. Or if you have one which is dedicated in your network and you would like just your CA to configure it for this device, you can just write the IP address of the certificate authority that you have inside your network. And in the end, I just send it back to you. So all of that, I'm just making the membership for you. After that, all our communication is totally encrypted. So even if people are trying to hack or trying to see what's being sent inside the network, it's totally encrypted. Not only this, it's encrypted by something called DIKE, or the encryption mechanism is DIKE. It's a new technology developed by Cisco, and it has less overhead than that of the IPsec. IPsec is always used for backwards compatibility. We are speaking about system till the beginning of 2015. That's the last time they were supported like IPsec. After that, everything is supporting DIKE. Cisco believes that the problem sometimes or misconfiguration comes from people, so here you cannot change anything. Here you cannot do anything. It just, you see the communication going, and you cannot access the interfaces, you cannot change such an order, you cannot do anything. We kept saying we write 5 commands. What are these 5 commands? It just, you say, this device will be registered. You will define the domain ID or the network ID. And if you would like to put the whitelist, if you don't put a whitelist, then every device will be accepted in your network. And after that, you will define what's the type of CA, the one will be issuing the certificates. Is it local, the same device, or you have a dedicated one and you can write its IP address? And that's all. After that, just no shutdown, just enable the services and autonomic. It's as simple as this, 3, 4 commands, and you have fully running network. And what do I need to configure? If I'm speaking about a brand new device, then none, nothing at all. And if this device or system has like a configuration from before, just one command, autonomic, and that's it. We are speaking about you will be configured. What's the configuration that you will receive? Well, you will have an IPv6 address interfaces will be defined for you. A VRF will be created for you, and tunnel interface for the secure communication. If you have a syslog TFTP server in your network, it will be just discovered on its own, so you don't need to define anything further. And even if you would like further configuration to be on the device, you just go to the TFTP, write the serial number of the device, and the device will just communicate with TFTP and download any further configuration. It just changes how we look into networks, changes the complexity. It's really that simple that you connect and everything will be automated for you. But the question comes after that. Are you in control? Do you really know what's running in the background? As per Cisco, we understand that we are in 3 phases, and we at least have a UDP service running on port 4936, and we have this DIC on port 5000. So I expect to see multiple phases or multiple types of packets. But what I see here is this. Well, this is LLC layer 2 technology. Wireshark cannot understand or see what's really running here. You have no idea what's really running inside your network. So what we will be trying to do throughout this part from the presentation is try to reverse engineer this, understand what are these packets. Well, this is the first packet or frame that we have. How do we start? I know that in the beginning we at least have an Ethernet frame, but which type of Ethernet? Well, we have 3 types. By checking here, we know it's not an Ethernet 2 frame, and by here we are sure that we are speaking about snap frame. So at least as the beginning, we understand how we start. We have destination MAC, source MAC, some frame length, the snap frame identifier, the organization identifier, which is OC for Cisco, and after that, the autonomic protocol ID. Okay, till this point, at least we managed to understand this, but what comes after is the autonomic protocol. And we believe that it can be understood or analyzed based on this header. We introduce this new header. We believe this one we can use to understand whatever comes after. To test this, we try to analyze what's coming further. We see here the version and the state. The state says in which phase are we in the protocol. This is the first frame, this is the first thing, so we're just in the first phase. Factory default, never change, and some opcodes. Opcodes means what's the function and significance of such a frame. What's the role this frame is playing throughout the whole communication. These are the available opcodes for the channel discovery. After that, we have the header length and some reserved bytes, then TLVs. For the available TLVs for the channel discovery, they are simple as that. We are just speaking about 1 or 2 frames being sent every now and then, either probes or keep alive, something simple as this. The adjacency discovery is a bit bigger because supposedly we expect a UDP header here. So we start with the same idea. This is the Ethernet snap frame, we already know that. But here is the problem. This is the one customized channel discovery header that stops Wireshark from analyzing the packets. This thing is the one that is added by Cisco. It's somehow like 2.5 layers for these autonomic services. To understand this, it's somehow very close from the one we have just seen, but just, however, the state is different here, which is O5 and ether type. This ether type means what's next header coming, and for this one, it's an IPv6 header. After the IPv6, we know this is a UDP header, just from analyzing what's written in the IPv6 header. And after that, we start again with the autonomic protocol. We believe that for the adjacency discovery, it's the same header. We can use the same header. We don't need to introduce a new header for that. And here the version is 2 instead of 1. The state is O2. We just started into the channel in the adjacency discovery phase. This is the first packet here. We have multiple states because either we are like trying to get your membership or trying to add you into the domain or even trying to build a secure channel. After that, the reserved bytes again and the opcodes. In this case, we have much more opcodes. Here are they. And after that, the header length, some factory default bytes, and TLVs. For the available TLVs, they are quite big. We would have needed like 3-4 slides just to put the available TLVs. So if there's a link in the end, if you are interested more in know all TLVs, you can just check it. And here comes a little bit of a challenge. A secure channel. What shall I do? It's totally encrypted. Port 5000, DIC. I have no control over this. What if I'm a little bit interested to know what's really running inside? What shall I do? Cisco is a black box device. I can't say which keys that they should use, for example. So the question is, if I'm really interested to know everything about this technology, how do I know what's really inside? And for this, please let me introduce you to this beautiful device, the ME3600X. It is one of the very early first devices to support autonomic network, starting in 2014. But the question comes, how can that help me? Well, as we said, we have an IPsec for backwards compatibility, and DIC is the brand new one. Also, I cannot control IPsec. How can, even if I have an IPsec, how can I see what's being sent inside? But you know what? From the RFC, there is IPsec null. In other words, IPsec without encryption at all, just authentication. And if we implement this, then we can see a packet that's truly unencrypted within the tunnel itself. This packet is the RPL. RPL is the routing protocol of autonomic network. It can never ever be seen outside of the tunnel. Supposedly, it totally should be encrypted and never be seen. We can see such information here that we are using GRE and some ESP and some stuff. So it appears to be going fine. Everything seems to be good. The encryption is, or whatever it is, DIC is a brand new one. There are no attacks against it. The question comes, is this technology really secure? Can we start deploying it? Can we start putting it into action and see how we can build networks in just 10 minutes? And for that, I thought about, let's do it, try to do it live, and see whether they will withstand some of the attacks that we have in mind or not. And if we have any problems, I believe a live support can help us. So anything that happens, we will try to write to them and see how it goes. So the first idea I had on my mind that while we are speaking about, they said that two different devices from two different domains cannot communicate together, or at least they will be neighbors. So what I'll try here, even as a basic thing, is try to connect to a device which is from a different domain and see how it will be. So this is from different domain. Its domain name is malicious, as we see here. And my register or my device is from domain ERNW. So supposedly, they never should be able to communicate together, or at least they will be neighbors. So I'll try to put this into test. I'll get this, I'll try to connect, go to, and see how it will go. So I see they became neighbors. Well, this is expected. And can even see that some configuration is going back and forth between them. And although this shouldn't be, we have built a tunnel. We have built a secure communication with the devices within our domain. Come on, we are speaking about device which is somehow maybe be malicious. It shouldn't belong to my domain. It shouldn't belong to my network. So what's this about whitelist and what's this about everything? I need to write this to support. Hey, I try to connect two devices from two different domains, and they communicated together. What do you think about that? Honestly, from Cisco perspective, they were quite responsive to all the vulnerabilities that we have disclosed here. Then they were quite fast enough to even to think and just pass our request for the business unit. So the business unit, the designers said, well, you know what? If they belong or their certificate was signed by the same CA, they can join. They can be in one domain, or they can communicate together. But come on, this is not as per the specifics. This is something that we didn't expect. Yeah, don't make a big deal. We will just add this feature in the future. Okay. What's the significance of that? If the device has a certificate, we never check our whitelist. So this device will be always able to communicate or be inside your network. There is no way you can stop such a thing, because this certificate will always be passed. But you know what? What I can do usually simply is I go to my register here and just try to, this is the domain name of the server, and just try to revoke the certificate, saying this certificate is no longer valid. Well, I tested here on a local CA, and when I went to Cisco and said, well, I tested here and it didn't work, they said to me, you know, we don't support it for local CA. I said, but also I tested for external CA. What do you think of that? They said, okay, oops, this is a CVE then. So what's the significance of such a thing? You cannot protect your network. You cannot revoke the certificates. If there is a device, an old device from wherever it is, that has a valid certificate, it can always be part of your network. If you'd like to protect yourself, you need to remove the keys of your CA and make new ones. Best of luck. Okay, I see a little bit scary, but you know what? I'm the one who has control over my network. I'm the one who controls my CA. I generated the keys privately, and I don't care about such problems. As long as the communication is stable, that's all what I care about. Even if we go to the register here, we can see that the communication has been up for around 3 minutes here on both. Yeah, 3 minutes here, 3 minutes here. So I don't care about such problems. What can someone maybe do? What if someone tried to reset the channel for you? Let's see. Okay, I see my device has been affected, but okay, this is not good. I see the interfaces are coming down. There is no longer a secure or stable connection. Anyone passing by can just attack your network. This is not good. Let me check how long is something changed here. Yeah, they are down. And because we have here self-healing, these devices should now restart or try to build the tunnels again on their own. But in other words, anyone passing by can just break the stability of your connection. We can see here that the interfaces and stuff come up on its own. This is the idea of self-healing. But there's more here said, like check your Wireshark. What's really scary about this is this. This is the RPL. This is what should have been encrypted. So on breaking your channel, not only the connection breaks, but everything inside that communication or secure channel is sent in plain text. So there is no encryption. So no stability and no encryption. This is quite scary. And as usual, we have the live support with us for that. Sorry. Something like the attacker can reset the remote or secure channel and can see everything in plain text. What do you think? Yeah, it's another CVE. Come on. So what's the problem of this? We start into the phase that you can never have a stable, secure connection anymore. But you know, I still believe in autonomic network. I believe it's just one problem that they can solve. Although when you read the advisory from Cisco for this vulnerability, you will find that they wrote the vulnerability is due to unknown reasons, and we don't know how to solve it, and we don't have a workaround for that. So it's still like a zero-day attack. So anyone who, they will solve it later, you know, don't worry about it. All what I'm afraid about now is my devices at least are running up and stable easily. But for this, I have this small video. In this video, I just try to reset the channel multiple times. Keep resetting the channel one after another. And if we see here that I'm trying to ping after that, well, this is a little bit scary because it means that even devices can crash. Well, I just tried. I just wanted to put it into test and see whether it will withstand or not. So I just enjoy watching the video with you. This is what happens. If you keep resetting the channel multiple times, this attack can take quite some time, around 15 to 20 minutes just to do it. But devices crash in the end. I'm back to the life support command. So if the attacker kept resetting the channel for multiple times, eventually the device will crash. And for this, we have another CVE. So it just takes around 15 minutes to do it. And up to now, it's the same problem for unknown reasons. And there is no workaround around this. And still valid attack. But no, at least autonomic is not that bad. You know, I have my register, which is somehow the strongest device in my network, and no one can touch it, right? Yes, let's go to my register. Here's the register. It has been up for how long? Let me see. It has been up for 1 hour. Come on, at least this is the strongest thing in my network, right? And no, I cannot crash the register simply like, okay. So, this is not good. Support. Sending space or null as the enrollee name will crash the register. I don't have anything more. Honestly, the register is crashed, the enrollees are crashed. So I'll just disable autonomic network. Sorry for that. I don't have any other option. So this one is already dead. So I'll try to connect to here. Connect here. Well, this is my new device. I'll just, sorry, I'll just disable autonomic network. I'm afraid of that. I'll just configure it as you configure any normal device. Like I'll just give my interface an IPv6 address and live in peace. Something as simple as maybe like as this. And even, you know what, I will just go to my second device too. Because, yeah, I like the technology, but I need my devices. I'm sorry. No autonomic tool. And I just configure it normally. Yeah. At least, you know, now I'm safe. I'm safe. Fine. I will write it even for you guys. I'm safe. Nothing can touch my devices. Nothing can do any harm to my attack. At least, oops. So, I even haven't configured anything on the new device except the IPv6. Well, honestly, this is my favorite attack. I like to call it the death kiss, because it's just one packet to destroy completely your device. Crash it wherever you are. Just knowing your IPv6 address will crash your network. For this, in order to protect, either to upgrade to the new operating system or the new iOS image, or just put an access list on each and every interface, even the loopback interfaces, dropping anything coming on port 4936 or 48. Else, you will always be vulnerable. It's not local, it's global. You can be here and crashing people in Australia. To conclude today's presentation, we have spoke about autonomic network. We spoke about these 3 phases of the communication. We spoke about 5 vulnerabilities here. One of them, just need your IPv6 address, no further configuration, nothing, just to totally crash it. Finally, if you would like to get your hands dirty, work with such stuff, I recommend WireEdit. It's the first application that used our analysis, and now you can use it. It wrote a dissector, and you can use it there. And you can download the free image for Cisco CSR 1000V. And I wouldn't have done this without the help and assistance of Mark Eissa. He helped me so much with the protocol analysis. And finally, if you're interested more in knowing more, you can just check insinuator.net. You will find there the introduction, analysis, and conclusion, or all the vulnerabilities that we spoke about. I hope you enjoyed today's presentation, and thank you.